Okay, so we're going to take a look at section 1.3 on trigonometric functions. We'll talk more about what trigonometric functions are in a little bit, but first I want to talk about a couple things that I think you've seen before, but just to make sure you're familiar with it, I'm going to talk about it again. Mainly the Pythagorean Theorem. Okay, so the Pythagorean Theorem basically says if you have a right triangle, remember a right triangle must have a right angle in it. If you have a right triangle, the two legs, or the two sides adjacent to that right angle, we're going to call A and B, or they have length A and length B. The hypotenuse, opposite the right angle, has length C. Then the relationship between those three sides is A squared plus B squared equals C squared. Okay? This relationship is always true. It can be proven in a variety of different ways. I'm not going to go through and prove it here, but just know that this relationship is always true. Now that that's established, let's take a look at a situation where we take a right triangle and put it on a set of x and y axes. Okay. So let's write out a set of axes. Okay. There's an xy axis, and then throw some arrows on here. Okay. And then we're going to make the triangle sit so that one side is along the x-axis and one vertex is at the origin. There's a vertex at the origin. It's going to go up at an angle. Just send it out to the right somewhere. And now somewhere along this line, I'm going to choose a point. It doesn't matter where that point is exactly, but we'll just put one right there. I'm going to call that point the point xy. Okay. Now it could be any point on the line, doesn't matter. But if I were to construct a triangle by then dropping a perpendicular line down to the x-axis, then I've created a right triangle where one side is along the x-axis. If the coordinates of this point are x comma y, then the horizontal side of the triangle has length x, and the vertical side of this triangle has length y. Okay. Now the hypotenuse, we're going to give that a name as well. We're going to call it r. And I've always assumed the r stands for radius, because we'll be dealing with circles in a similar context in the next chapter. Okay. So we've got x, y, and r as our three lengths. And of course the Pythagorean theorem would tell us that x squared plus y squared will equal r squared. I'm going to get rid of these labels. Okay, x squared plus y squared equals r squared. That's the Pythagorean theorem. Okay, so that gives us a relationship between the sides. Now remember from the last section, from 1.2, that when we have similar triangles, there's a theorem about similar triangles, that the ratio of corresponding sides is always equal. So how is this important? Well, if I were to draw actually let me draw a little bit different diagram here. I'll erase what I have, because I'm going to need a little more room to draw some more triangles. So let's put the xy axes way over here now. Bottom left corner. And we're going to draw hypotenuse. I'm going to draw one point here. There's my side going down to the x-axis. And now let's say I put a second triangle in there. So I pick a point. Let's pick one right here. And we'll bring a perpendicular side down there as well. And so because these two are parallel lines, we have similar triangles. We discussed that in the last section. Okay, so we have two similar triangles. What's interesting is if I label these triangles two different things, let's label the first one with the point x1, y1. Okay, I don't know if you can see that real well. The second point is going to be labeled, oh, right, this is a little bigger, x sub 2, y sub 2. Those are subscripts on the variables, okay? Then, oops, I should have done that one in black. I don't know if you can tell the difference real well with the lighting, but it bothers me to not be consistent. So x2, y2, okay? All right, and so the hypotenuse of each of these, we'll call them R1 and R2 correspondingly. Okay, so R1 is in blue here. And R2 is the entire length of that side. So I'll put it up here. But it really represents the entire length, not just a little segment up the top. And so there's a couple main relationships here with the Pythagorean Theorem. We know that R2 squared is x2 squared plus y2 squared. That's all the coordinates off of the bigger triangle. We also know from Pythagorean Theorem that R1 squared equals x1 squared plus y1 squared. That's the three coordinates off the smaller triangle. Okay, what else do we know? Well, we know that ratio of corresponding sides is always equal. So I could do the vertical side of the big triangle divided by the vertical side of the small one, and then the hypotenuse of the big one divided by the hypotenuse of the small one. Those will always be equal, those ratios, okay? There are 6 very important ratios that we're going to talk about in this class, and from here on out, we'll pretty much be talking about them every day, okay? Because those corresponding ratios, the ratios of the corresponding sides are equal, let's set up some of these ratios. The first one I'm going to set up is the ratio between y and r. So there's a ratio, that you could do y2 over r2. Oops, I don't want to square that one. Should be a subscript. So y2 over r2, and we could have y1 over r1. So it's basically the vertical side divided by the hypotenuse, or the vertical here divided by the hypotenuse. Those two are equal, those two fractions are equal because they have corresponding sides in the same position of the fraction. Okay. And it doesn't matter how big or small I make these triangles, as long as the angle is the same. Okay, as long as I have a fixed angle here. Now the angle, I am going to put in here as the angle theta, okay? Now theta looks like a circle with a bit of a slash or curl through it. Theta is a Greek letter that we often use to represent angles. Okay, so just up to the bottom here, theta is that symbol, roughly speaking, that looks like a 0 with a slash, and it represents angles. At least we're going to use it for angles quite a bit. Okay, so anyway, as long as that theta is fixed, the angle isn't changing, then the ratio of the vertical side to the hypotenuse will always be the same. That ratio, y2 to r2 or y1 to r1, we're going to give it a name because it's the same no matter how big the triangle is. The name for that is the sine of theta. Okay, the sine of theta, S-I-N-E, of theta, which is abbreviated as S-I-N theta. Okay, that's the abbreviation. Is always going to be equal to the y, or the vertical side, divided by the r, which is the hypotenuse. So it's vertical divided by hypotenuse. Okay, in this example. Now there's other ratios, right? So if I did the vertical divided by the hypotenuse, you could imagine, well, what about the horizontal divided by the hypotenuse? Well, that's given a name as well. That's called the cosine. And we abbreviate that with cos theta. And the cosine is going to be the horizontal side x over the hypotenuse r. So it's x over r. In fact, I'm going to rewrite those, give myself a little more space. Kind of write those on an angle there. Okay, so y over r and x over r. So we've compared each of the two legs to the hypotenuse, but what happens if we compare the two legs together? Okay, well, the two legs combined together, if I do the vertical side to the horizontal side, we call that the tangent. That's the y over x. Okay, the tangent of theta. All right, so that gives us three of those ratios. Now there are three other ratios. They all happen to be the reciprocals of these three, right? So I have the combinations together, right? I've got y with r, y with x, and x with r. But what I don't have are flipping them, so the order's different. Erase a little bit here. So our three, the three other ones are going to be what we call the cotangent of theta. And so the cotangent is the reciprocal of the tangent. Okay, so you'd have, that's equal to the cot theta, which is x over y, okay, x over y. The secant of theta is next. The secant is the reciprocal of the cosine. Okay, so we call that, we abbreviate it as sec theta. And it's the reciprocal of the cosine, so it'd be r over x. Right? Finally, we have one called the cosecant. Cosecant of theta, and that's equal to, in the abbreviated form, cos theta. And of course, that's going to be the reciprocal of the sine. So look at the sine, flip that, it's r over y. Okay. So these are the 6 trig functions: the sine, cosine, tangent, cotangent, secant, and cosecant. Okay. Now, it's hard to memorize all 6 of these ratios. Very hard. In fact, I couldn't just memorize these right off the bat, I don't think. I mean, I could maybe, but I'd probably get an X or a Y swapped around somewhere. But I do expect you to know these. Yeah, so in order to do that, there's a saying that we use, and I'll explain that in a moment as we go. I'm going to get rid of these, the ones in blue here, the last 3 that I wrote up, because they're all reciprocals of the other ones. So if you know the other 3, you can get these just by flipping the fractions over. So I'm going to erase these for just a moment. And really I'm going to get rid of some of this other stuff too. Okay. Now, if you remember where or how that triangle was situated, okay, so here's my triangle. I've got theta, I've got the right angle. I'm going to have x as the horizontal side, y as the vertical, and r as the hypotenuse. You can always think of these using an abbreviation. It's called SOHCAHTOA. If you remember that, SOHCAHTOA is an abbreviation for these sides. You've got sine, cosine, and tangent all in the abbreviation. So S, there's the C and the T. The O's and the A's and the H's represent the 3 sides. The O represents the side opposite the angle. Okay. So if you notice in the sine, we have y over r. Well, y is the opposite side, and r is the hypotenuse. So we have sine is opposite over hypotenuse. Okay. So we'd say sine theta equals the opposite divided by the hypotenuse. E-N-U-S-E. Okay. So that's the opposite over the hypotenuse. Essentially, the y side, the vertical side, is the opposite here. And the x side is what we call the adjacent. Right? Because it's right next to the theta, the angle. And then, of course, the r is called the hypotenuse. And so that should help us to structure this. So we've got the sine is opposite over hypotenuse. The cosine is adjacent over hypotenuse. And the tangent is opposite over adjacent. Okay. So if you can remember this, SOHCAHTOA, and how to spell it and what they represent, then you'll have a much easier time remembering the 3 main trig functions. Okay, so remember this. You can figure out the 3 main trig functions. From there, you flip them to get the other 3. And remember that the tangent's inverse is cotangent, the cosine's inverse is secant, and the sine's inverse is cosecant. Okay, so what's interesting is that the cosine and cosecant are not opposite, or they're not reciprocals of each other. So the cosine is reciprocal of the secant, whereas the sine and the cosecant go together. Okay, they're reciprocals of each other. Okay. So now let's just do a couple quick examples, and we'll try to finish this off here. Okay, so here's an example. Let's say I had my xy axes, and I had a point over here at, let's go with negative 5 comma 2, okay? So my point's at negative 5 comma 2. Well, if I create an angle going through, from the origin through that point, the angle theta technically is coming up from the positive x direction. But I can again drop down my perpendicular line, and what we need to, what I'm curious to know are what the 6 trig functions are. Okay, so I want to know what is the sine of theta, and the cosine of theta, and the tangent of theta, and the secant, and the cosecant, and the cotangent. Okay, I want to know what those are. Well, I can do that because I know what the x, y, and r are, or I'm going to find them anyway. So let's look at the r for a moment. I know that r is equal, well, r squared is equal to x squared plus y squared. What's interesting is the x value is negative, and that's actually okay. We can have negative values in here. Now, one popular form of the Pythagorean theorem is to take the square root of both sides, so we get r by itself. So r is the square root of x squared plus y squared. Now I know what x and y are, so I could plug those in. So r is the square root of, well, x is negative 5. Negative 5 squared is 25. So 25, and then the y is 2. 2 squared is 4, and 25 plus 4 is 29. So I get the square root of 29. Okay. So that's going to be the r value. Whoops. Square root of 29. All right. And so when I come up with my 6 trig functions, I want to again remember the SOHCAHTOA. SOHCAHTOA. That's my abbreviation. And so I'm going to go ahead and do the cosine. I'm sorry, let's do the sine first. Doesn't matter really. Okay, so the sine of theta, remember sine is opposite over hypotenuse. Well, you could also think of, consider the angle really being this small angle. That's the one we're looking at. Even though theta is on the outside of the triangle, that's okay. So the opposite is the vertical side, that's 2. And the hypotenuse is the square root of 29. Okay, so it's 2 over root 29. Now, in the last video, I showed you how to rationalize denominators. We're going to do that again. And so, to do that, I'm going to multiply top and bottom by the square root of 29. Let me rewrite that so it's a little bigger. I'm going to get 2 over square root of 29. I'm going to multiply top and bottom by the square root of 29. Then we're going to multiply across. So we're going to get 2 square root of 29 all over 29. Okay. And that's it. That's my sine. Okay. We can also work with the cosine, the tangent, and all the other ones. As soon as I know the sine, I should be able to do the cosecant immediately just by flipping it. Okay, so the cosecant, CSC theta, is the reciprocal of this one. Now if I flip this final answer, I'm going to move the radical back to the bottom and have to rationalize. I don't want to do that. It's actually easier to just flip the original fraction, because then the denominator, then the root will end up going to the top. So 2 over root 29 really will become root 29 over 2 in the cosecant. Okay. In a similar way, I could go through all of the different trig functions. So the cosine is the adjacent over hypotenuse. That's the x over r. The x is -5. So cosine theta is -5 over the square root of 29. Right, so that's x over r. And of course negatives are okay. And I need to rationalize that denominator, so again multiply by root 29. And we're going to get -5 root 29 all over 29. Okay. So that's the cosine. Now the secant, we've already talked about that. Secant theta is the reciprocal. I don't necessarily want to flip the last answer because that again puts a root on the bottom. So we're going to flip the first answer before it's rationalized and call it the square root of 29 over -5. That's our secant. And then of course you still have the tangent and the cotangent to deal with. The tangent of theta is the opposite over the adjacent. So we go tangent is opposite, which is 2, over the adjacent, which is -5. Okay. And of course 2 over -5 is what, -0.4? Okay, so that's our tangent if I wanted to simplify that. Or -2/5, however. And then the cotangent, COT. Cotangent is the reciprocal of this, so you flip that and you get -5/2. And of course 5/2 is really 2.5. So we call that -2.5 if we wanted to. Okay. Alright, we're going to pause this, go to the next video, and we'll finish up a couple other things.